got to figure out which one pertains to what you're going to be doing in your project, okay? So you remember this z-test? It required you to have quantitative data. You had to have a relatively large sample size, 30 or higher. And then you had to know, like, for example, the population standard deviation. Because if you don't know that, how are you going to calculate this, right? But what if you, like, what if you don't meet those conditions, okay? And that's possible. That's possible because not every scenario you're going to know the population standard deviation. What if you don't know it? What if you can't estimate it, right? Or, even more common, what if you have a small sample size? So, or you could violate both of these conditions. Can you still do the test? Yes, but you have to do the t-test, okay? So, you remember this example? From when we first started hypothesis test, we did the z-test on this, and like here's that was the population standard deviation we used, and then here's the sample size 40. Well, let's make this a little bit more realistic. What if we don't know this value? What if we have a small sample size, but we still want to determine whether or not if the true population mean is higher than the claim of $37,318. So now I'm gonna give you a new scenario, okay? I'm gonna give you this. Suppose you know the average win is $37,318. Don't know the population standard deviation, and you only have 17 data values, okay? You still want to do this right tail test, okay? And you want to determine if the true mean is higher than this value, right? So, there's the data. You only got 17 observations, okay? Now we have to use a different hypothesis test. It's going to use a different distribution called the t-distribution. Now, here's where, okay, so doing the test is not hard. It's similar to what you did for the z-test. Here's the challenge, though. The t-table is completely opposite of the z-table. So can you do me a favor? Pull out the z-table also. You'll see what I'm talking about. Let's go back and look at the z-table really quick. Okay? And put them side by side for me. Put the z-table to your left. Because I'm going to ask you some questions. All right? Okay. What do you see? Look at the figure. Look at the picture that is on both tables. The z-table and the t-table. What is similar about those distributions? They're both what? Bell-shaped is the correct answer. They're both bell-shaped. Okay? Now, but now what is different? Look at the z. Right, on the z-table, you got probabilities to the left. The shaded region is going to the left. Look at the t. Right. It's going to the right now. Is everybody with me? All right. Now, both distributions, the center is still 0. Standard normal distribution, the center is 0. On the t-distribution, it's the same thing. The center is 0. Is everybody with me? And then look at the z. The z, you had 2 pages. One for the negative z's, one for the positive z's. You see that? T is only one table. Okay? It's only one. Now, here's the biggest difference though. The z, the probabilities are on the inside, and the z's are along the edge, right? Yeah. You see that? Look at the t-table. It's backwards. The t values are inside of the table, and the probabilities are on the outer side. And more specifically, it's at the top. You look all the way at the top. Okay? You see those probabilities up there? That area on the curve is probability. Is everybody with me? So it's a little bit opposite how to use that table. Okay? And then we got to talk about where it say DF. That's called degrees of freedom, okay? We have to calculate that to figure out which like row we're using. You see what I'm saying? And then also with that t-table, we have to approximate the probability. It's not going to tell us the probability. So it's a little bit different from what we covered with the standard normal table, the z-table, okay? All right, let's keep going. So here's what we're going to do. I'm going to show you how, I'm going to show you how to do this test using StatCrunch. We're going to put this data in StatCrunch, and then we're going to just run the analysis. But I'm going to show you how to set up the known and alternative, how to do the 5 parts of the hypothesis. So, guess what? Setting up the known and alternative hypothesis is the same thing as how we learned with the z-test. So you either do what? Left tail, right tail, or two tail. So none of that changes, okay? And this, remember, this is symbolic notation, right? Of how to set up the null hypothesis and the alternative hypothesis, right? So left tail, you have a less than sign. Right tail, you have greater than sign. And then two tail, you have a not equal to sign, meaning you're doing left tail and right tail in one big test, okay? So that doesn't change. We covered that when we did the z-test. For this example, we're doing the right tail, right? Level significance, still the same. 5% unless stated otherwise. That doesn't change either, right? Third step, though, the observed test statistic. Now we can't use that z-score formula we saw. Now we have to use this. But it looks similar to the z, the observed test statistic for the z, right? Remember, it was z equals same thing here, sample mean minus population mean, but we had population standard deviation there, right? Now it's gone. We're using, what are we replacing that with? What is this? Sample. You're right. First word you should say is sample. What is S? Sample.
Mean.
Sigma. What was sigma?
Oh.
When sigma was here, what was that? That was what? Standard population, standard deviation. Now, instead of using right, sample standard deviation. That's right. This is sample standard deviation. So we're going to calculate the standard deviation using the sample data. Is everybody with me so far? All right. So it's still standard deviation, but we use sample standard deviation now. Divided by square root of the, what is that? Sample size, correct. Square root of the sample size. So we're using a test statistic formula that's pretty similar. It's close to the z test, the formula that we used when we did the z test. Okay. Now, to use this test, of course, you got to have quantitative data. And then this is normally assumed to be true. But the way you can test it, for this, you can do a normal probability plot. And we covered that back in the beginning too. Normal probability plot. You assume that the data comes from a population that's normally distributed. Okay. For the most cases, we're going to assume that this is true. But we could test for that using the normal probability plot. We take this sample data. We would take this, where is that? We would take the sample data and make a normal probability plot to show that it came from a population that's normally distributed. Okay, let's keep going. After you calculate this observed t-test statistic, you have to calculate the degrees of freedom. It's easy to calculate. It's just the sample size minus 1. Okay? It's simply just, you take the sample size and minus 1. Subtract 1 from the sample size. We call that degrees of freedom. Now, what is the degrees of freedom? It is a value that changes, that controls the shape of the t distribution. So the t, where's the t table? Let me explain something. Okay, thank you. So the t, how many of you know what X-Men, Mystique, she was shape-shifted. She shaped it to different forms, right? That's what the t is. The t is a shape-shifting distribution. Now, here's the pro. It always stays veil-shaped. But the degrees of freedom, as the degrees of freedom increases, the t distribution gets taller. okay? But it stays bell-shaped. But the higher degrees of freedom, the more the taller the hill, the mound, the bell. Is everybody with me so far? Degrees of freedom controls for that. Is everybody with me so far? All right. All right. So what else? What else? I was gonna say. Yeah. So yeah, degrees of freedom. That's the purpose of it. All right. All right. What else? See, look. So this is different. See, it always stays bell-shaped. You see what I'm saying? And look, as the degree, look at this green. Look at not green, the blue. Let's start with the blue. You see, the blue, that's the T distribution when you have 3 degrees of freedom. Oh, with 2 degrees of freedom. Because remember, degrees of freedom is 1 less than the sample size. So if n is equal to 3, the degrees of freedom is what? 2. Is everybody with me? So look at that shape. It's still bell-shaped, but not as tall as, look at the green one. And look at let's look at the red one. Red is here, it's taller. Look at the sample size, 12. So what's the degrees of freedom? 11. You see? And you see how the red one is taller than the blue? You see what I'm saying? Still bell-shaped, still T distribution. Now, when n is getting closer and closer towards infinity, positive infinity, okay, then look, it's at its tallest. You see that? Still bell-shaped. But it's at its tallest. And the larger the sample size, the taller the T distribution gets. And the higher the sample size, the more the T distribution turns into the standard normal distribution. Is everybody with me so far? Okay, so as you use a larger sample size, the shape of the T distribution gets taller, and when it's at its tallest, then it has the same form as the standard normal distribution. So in other words, is the bigger the sample size you use, the more that this T distribution, this shape, turns into the shape of the standard normal distribution. Still bell-shaped, but they turn into one and the same. That's what I'm trying to say. All right?
Which one changes?
The T. T is the one that changes. T is the shape-shifting one. And it depends on the degrees of freedom. But notice for all of these cases, the center is what? 0, right? And if it's bell-shaped, what does that mean? For every positive T, there's a, on the opposite side, that is equidistant to the center. Is everybody with me? So for example, if there's a T value of 3.2 here, that cuts off this amount of area, there's a negative 3.2 on this side that cuts off the same amount of area going in that direction. Is everybody with me so far? Because this is a symmetric distribution. All right? Does everybody see that now? Isaac, go ahead.
For the formula.
You have to talk a little bit louder, Isaac. I'm sorry.
For the formula, is the mean still the null mean?
This one is here.
Yeah.
Yes, that mu is the value that you're fighting over in the null hypothesis. So the value that you're fighting over here. See, look, mu is equal to whatever that value is, right? So you're going to replace mu naught with the value that you are fighting over in the null based on the scenario. Yes.
But what's assumed?
Right. Correct. So y'all clearly see we're doing the right tail test. For that first example, we're doing the right tail test. So mu naught in that example is the what? The 37,318. That's right. Mm-hmm. You're right. Mm-hmm. All right. Okay. Let's keep going. Now, so as I told you, so just to recap what we said, unlike the Z table, the student T table is controlled by the degrees of freedom. Okay. All right, and the T values this time are inside of the table. These are not probabilities. These are T values. The probabilities are up here. Is everybody with me? So the bad thing about this T table is that you have to approximate or interpolate what the probability is. You see what I'm saying? Okay? So you have to estimate or interpolate the probability. Okay? And you'll see what I'm talking about when we actually use this table, so hold tight. The shape of the student T-curve is also bell-shaped, centered at 0. For every positive T, there's a negative T on the opposite side of the curve. All right, we just talked about that, right? All right, so you're like, well, how do we calculate the p-value? Now, of course, we're going to use StatCrunch, right? StatCrunch will tell us the probability. But if we use the t-table, it's going to approximate the probability, okay? We have to approximate it using the table. And then this stays the same, just like when we did the z-test, right? To find the p-value, when you do a left-tail test, you find the probability to the left. If you do a right-tail test, the area under the curve to the right of our observed test statistic is our p-value. Two-tail, we have to find the probability to the left, probability to the right. Keep the one that's the smallest, double it. Remember, once you find one, the other is just the complement, right? But you keep the smaller of these two, and then you double it, and then that's how you calculate the p-value. When you do a two-tail, test. And then finally, last step, if the p is low, the null must go. So if the p-value is at or below the level of significance, you reject the null hypothesis, okay? All right, let me say this. This is always going to apply for every single hypothesis test that we're going to cover. This always applies. So that's why I was telling you there's this saying, if the P is what? The null must. That applies for every single hypothesis test we're going to cover in this class. Is everybody with me? The smaller the p-value, the more evidence to reject the null hypothesis. The smaller the p-value, the more you are inclined to say guilty. Is everybody with me so far? If you want to think like court, okay? Like you do in court. All right, so going back to our example, here are the 17 observations. Oh, can we put in StatCrunch? Okay, we'll put in StatCrunch. Okay. Oh, do we need to take a break?
Reject
Okay.
the null, right?
No, I just want to make sure. If you got a pee or boo-boo, let me know. Okay. So let's finish out this and then we'll take a break. Let's finish this out. Okay. All right, so how did I get these values? Okay. Let's go. I'm gonna pull this up because I'm gonna need this data. Or you know what? Let me stay here. And let me just get the lecture notes. Go ahead and open up StatCrunch. You making the data values. Y'all ain't gonna make me do it and leech it off me. No, you do it. So open up StatCrunch and enter in the data values, those 17 data values. And then I'm going to show you from the output.